Find the minimum distance from the point 406 to the plane x minus y plus z equals 3. So you have some plane in space that's given by that equation. And I'm assuming the point 406 doesn't actually belong to the plane. Otherwise that would make a boring problem. So if you wanted to know the distance in space between a point xyz and the point 406, this distance is going to be given by x minus 4 squared plus y minus 0 squared plus z minus 6 squared, and then you would take the square root. In other words, this would be the norm of the difference between those points. And we did this at the very beginning of the semester, where we calculated the distance between points in space using that formula. But if all I'm trying to do is minimize the distance, I don't have to specifically minimize just the distance. There's a neat trick where if I square the distance, then finding the minimum of the distance squared is the same thing as finding the minimum of the distance. The minimum of the distance squared is the same as the minimum of the distance.
So with this formula, it works for 2 points, not a point in a plane.
True. It does. But I haven't specified what this point is. What I'm about to do is I'm about to constrain x, y, and z to belong to that plane. Yeah, so you're on the right track. Yeah, you're anticipating my next move. So yeah, so I need x minus y plus z equals 3. And so I'm just going to rearrange this a little bit and write y equals x plus z minus 3. I'm taking my equation for the plane, where x, y, z, that point has to belong to this plane. I'm just rearranging it to get a formula for y. And then, in my equation for distance squared, where I have y squared, I can just pop in x plus z minus 3 squared. And now that I've used that constraint, that constraining relationship between my variables x, y, and z, since I've used that here in this equation, now I'm guaranteed that my solution, whenever I find x and z, it's going to belong to that plane. And then I can also use this formula to find the corresponding value for y. So I'm going to simplify this by expanding everything out. Like x minus 4 squared is going to be x squared minus 8x plus 16. This next thing squared is a little bit tougher to do, but we can do it. It's going to be x squared plus xz minus 3x plus xz plus z squared minus 3z, and then minus 3x minus 3z plus 9. And then plus z squared minus 12z plus 36. Ugh. Nasty. So now we collect like terms, so I'm looking for x squareds, and I see 2x squareds. I'm looking for x's, and I see negative 8x minus 3x minus 3x So minus 14x. As far as constant scale, I've got plus 16, plus 9, plus 36. That's 45 plus 16, so that's 61, I think. And then okay, I've got xz appearing twice. And then I've got z squared appearing twice. And then I've got minus 18z. And I'm done. Again, this is my distance squared, and so this is what I'm trying to minimize. If I can minimize distance squared, it's also the same as the minimum distance. So now I'm trying to choose values for x and for z that give me a minimum value of this nasty function. So I know that the minimum of this function of two variables has to occur at the point where the partial derivative of this function, I'm going to name it f, with respect to x is 0, and at the same time the partial derivative with respect to z is 0. Because this is the same as setting the gradient of f equal to 0. So these are my critical points, and I know that maximums or minimums have to occur at my critical points. So, the partial derivative of f with respect to x is going to be 4x minus 14 plus 2z. The partial derivative with respect to z should be 2x plus 4z minus 18. This gives me two linear equations with two unknowns. I'm going to rewrite this like 4x plus 2z equals 14. And then 2x plus 4z equals 18. I'm going to divide the first equation by 2. And that would just give me 2x plus z equals 7, and then I could subtract the second, I'll subtract that equation from that equation, right? So 2x minus 2x is 0, 4z minus z is 3z, and then 18 minus 7 should be 11, so that means z is 11/3. Since z is 11/3, that means that 2x plus 44/3 is equal to 18. If I divide everything by 2, that means that x is equal to 9 minus 22/3. And 9 is just 27/3. So that's 5/3. So x is 5/3. So I know x is 5/3, z is 11/3, and then that means y is going to be 5/3 plus 11/3 minus 3 minus 9/3. So that's going to be 16/3 minus 9/3. So y is going to be 7/3. And so this gives me the point xyz that is closest to the point, what was it, 406? Oops. Yep, 406. So, what did I say? 5/3, 7/3, 11/3. This is the point that is closest to the point 406, while it still belongs to that plane. Yeah. So now the problem is you would want to find the distance between this point and the closest point on the plane, right? In order to find what the question is asking for. The question is asking for the minimum distance. And so to do that, you would subtract these. You would do 4 minus 5/3, 0 minus 7/3, 6 minus 11/3, and you'd get a 3-dimensional vector with the distance in the x direction, the distance in the y direction, the distance in the z direction. And then you would take the Euclidean norm of that vector to find the distance.
You just plug it back in the formula.
Yeah. So what you would do is you would say, here, my x is now 5/3. My y is now 7/3. My z is now 11/3. And then this is the formula for my distance. Now I know what x, y, and z are. And so that is what you would have to calculate to solve that problem. So what I used here was basically just my knowledge that the minimum has to occur at a critical point, and then I found the critical point of my function of two variables. I didn't actually characterize the critical point, and I didn't really characterize the critical point because I only found one critical point anyways. And I sort of knew that it was going to be a minimum just based on geometric intuition. Like, I knew it wasn't going to be the maximum distance, right? If you think about a plane in 3D space and a point, there's no maximum distance. You can always find a point on that plane that's farther away from a given point in space. But there's only one point on the plane that's the closest point.